our PDs with VMO coefficient and application to SPD.
Thank you for introducing me. And I truly appreciate the opportunity to talk here, and I'm really grateful to organizers. This is a joint work with my chair, Professor Kyung Kim and Professor Ki Jung-lee. In 1996, Professor Kirov constructed an LP theory of this type stochastic partial differential equations. And here, coefficient Aij can be random and continuous for x, and noise is infinite summation of Brownian motion. For details, please see Professor Kirov's paper, whose name is An Analytic Approach to SPD. After his work, many mathematicians have developed Kirov's LP theory for more general domains and for more general operator and noises and so on. For instance, Professor Kirov and Professor Lotosky obtained this type LP theory in a half space. And Professor Kyung Kim and Professor Kirov obtained this type LP theory in zero domains. And Professor Kyung Kim generalized its domain to non-smooth domains. And Professor Jianqing Chen and Professor Kyung Kim obtained this type LP theory with rapid process noise. And Professor Dongdong Chang and Professor Ki Jung-lee obtained this type LP theory with the fractional Laplacian operator. And Professor Kyung Kim and Professor Pan-Gi Kim added a random coefficient to fractional Laplacian operator and generalized its noise to infinite summation of rapid processes. And Professor Mikulevicius and Professor Travaskas extended the fractional Laplacian operator to an integral differential operator. And Professor Kyung Kim and Professor Ki Jung-lee obtained the LP estimation of stochastic partial differential systems. Here's the history of SPD. Why do we need to study weighted LP theory? The need of introducing weight comes from the theory of stochastic partial differential equations. When we are considering this SPD in a half space with a zero boundary condition, by some examples, it turns out that going to better smoothness of solution is not possible in subgraph space without weight. So one needs to consider subgraph space with weight, allowing derivatives to blow up near the boundary. The idea of the introduction of weight is very common in the theory of partial differential equations when we consider boundaries or boundary data which are not very regular, or when we want some kind of degeneracy near the boundary. And even in the whole space, the same idea can be applied for stochastic partial differential equations when we deal with growing coefficient. For instance, please see Professor Jones and Professor Kirov's paper. When it comes to coefficients, SPD is strongly related to PD theory. Before explaining these relations, we introduce VMO coefficient and some history of LP theory of PD. VMO coefficient. VMO is an abbreviation of vanishing mean oscillation. We say Aij is in VMO if and only if the averaging integral of absolute value of Aij minus its mean goes to 0 as I goes 0. This is a generalization of a uniformly continuous coefficient. And VMO coefficient means that there are gamma and R satisfying this inequality. Actually, to get some solvability in PD, gamma should be small enough. And VMO X coefficient, which is measurable in T, and VMO with respect to spatial value of X. Define oscillation X like this. And here, there is no difference with respect to time variable. And define A sharp, the supremum of its oscillations. Then we say that Aij is in VMO X if and only if A sharp goes to 0 as R goes to 0. And partially VMO or VMO coefficients, roughly speaking, the coefficients Aij are measurable with respect to x1 coordinate and are in VMO for other variables. For details, please see Professor Do-Young Kim and Professor Kurov's paper. And variably partially VMO or VMO coefficients. This is a generalization of partially VMO coefficients. Very roughly speaking, the measurability of AIGA is given to other direction instead of on x1 direction on each ball. For details, please see Professor Kurov's paper. Let me introduce some definition of equations for people who's not familiar with PD. This is a non-divergence elliptic equation, and this is a divergence elliptic equation, and this is a non-divergence parabolic equation, and this is a divergence parabolic equation. Every coefficient AIGA satisfies this elliptic condition. For constant and uniformly continuous AIGA, LP theory of PD has been studied by many mathematicians for a long time in various ways. In 1991, Professor Chiavenza, Fresca, and Longo obtained the solvability of elliptic non-divergence equation with the VMO coefficient. And in 1993, Professor Bramati and Serati obtained the parabolic non-divergence equation with the VMO coefficient. And in 1996, Professor Di Fazio obtained the divergence equation with the VMO coefficients. And in 2004, Professor John and Professor Wang obtained the divergence equation with the VMO coefficient in Reichenberg domains. And in 2007, Professor Kirillov constructed an LP theory with the coefficient which is measurable in T and VMO in the spatial variables. And in the same year, Professor Do-Young Kim and Professor Kirillov obtained this LP theory with the partially VMO coefficients for P which is bigger than 2. And in 2009, Professor Kirillov obtained this LP theory of the non-divergence equation with a variably partially VMO coefficient for P which is bigger than 2. And in 2011, Professor Hongji-do obtained this type LP theory of the non-divergence equation with a variably partially VMO coefficient for P which is bigger than 1. And in the same year, Professor Hongji-do and Professor Do-Young Kim obtained divergence type partial differential systems with variably partial VMO coefficients.
Previous page, please. I have a question.
Yes.
For divergence case, I'm not don't know why here VMO assumption is needed for. In divergence case, there's no. Is it VMO with small?
Yes, small VMO.
But for divergence case, we actually have solvability.
For all P. LP.
For all LP.
Yeah.
Okay.
For all P.
Thank you. And then, can we generalize coefficients of SPD as much as PD? Suppose that we can solve the following two equations. So equation 1 is SPD, which is called the Marder equation. And equation 2 is PD. First, we solve SPD equation 1. And for each omega, we solve equation 2 with F equals delta V minus Aij V. And we define U bar as V minus W. Then U bar satisfies this SPD. So we can generalize the coefficient of SPD. Therefore, by using PD theory, we can easily extend the coefficients of SPDs. But when we treat SPDs in a half space or single domains, as I mentioned before, we need the appropriate weight near the boundary. So we need some weighted LP theory for parabolic PD to generalize the coefficients of SPDs in a half space or single domains. So let me introduce definition of a weighted solvable space. Before introducing this space, we need to know Bessel potential space. Here is a definition of Bessel potential space. For P, which is bigger than 1, and gamma, we define the space of Bessel potential H gamma p as the space of all generalized function satisfying this property. And fix the non-negative function zeta satisfy this property. And for theta and p, which is bigger than 1, and gamma, we define a weighted solvable space H gamma p theta as the set of all generalized function satisfying this property. It is known that even if we change zeta to another function which satisfies same condition, the space H gamma p theta doesn't change and they are non-zero equivalent. So this space is already defined. For non-negative integer gamma, there is an alternative definition. We can also define H and p theta like this, and it is known that this norm and the previous norm are equivalent. For details, please see Professor Kurov's paper. Here are related earlier works. In the 1960s, for specific theta, p, and gamma, this time weighted solvable space was studied by Professor Griswold and Lyons and Magins. And in 1999, Professor Kirov obtained the general weighted solvable space theory for general theta, p, and gamma. And in the next year, Professor Lotowski extended and generalized this theory to a general domain and solved some degenerative analytic equation in this weighted solvable space. And in 2004, Professor Kevin Kim and Professor Kirov solved the parabolic and elliptic equations with the continuous coefficients in C1 domain on this weighted solvable space. And recently, Professor Kevin Kim and Professor Kijoni obtained a weighted LP theory for second-order elliptic and parabolic partial differential systems on a half space. Here is Professor Kirov's result. Here, gamma is very general, and coefficient aij only depends time variable t. Then we can solve this equation in generalized sense. And for the solution, we have this estimation.
Did you click on M?
Yeah, here.
So
Here. MH gamma p theta. This is the definition. We can similarly define this space. So we can, and similarly to VMO without weight, we can define VMO coefficient with weight. We define oscillation theta x like this. Here, we change the Lubin measure to weighted measure nu. So we say A is in VMO x with weight if and only if supremum of oscillation theta x goes to 0 as R goes to 0. Similar to half space, we can define a weighted solvable space on C1 domain. Let omega be a bounded C1 domain and rho be the distance function from the boundary. Then it is known that there is a bounded real valued function psi which is comparable to rho x, and for any multi-index alpha, supremum of this value is finite. This is a known result. And take the non-negative function zeta, satisfy this property. And we define some sequence of functions. We define zeta n x equals zeta e to the n psi x. Then we can easily check that this sequence of functions satisfy these properties. And we can define for theta, gamma, and p, which is bigger than 1, weighted solvable space H gamma p theta as the set of all generalized function u on O satisfying this property. It is known also, this space is well defined. Similarly to half space, if gamma is non-negative integer, then these norms are equivalent. Here is Professor Kyung Kim and Professor Gi-jung Lee's result. Here, coefficient Aij is in VMO without weight inside domain. And coefficient Aij is VMO with weight near the boundary. Some kind of digit. And here, equation is non-diagonal equation, and they solve this equation in generalized sense. And for this solution, you have this estimation. Here are some notations, a little complicated. Here is our result. The setting is similar to the previous theorem, but here the equation is divergence equation. And for this solution, we obtain this estimation. Then let me sketch how to prove this theorem. Actually, we follow the steps which Professor Kirchhoff used in his paper without weights. First, get some local LP estimation with Aij. And second, relate the sharp function of U with the maximal function of F and U. And finally, apply Hardy-Rideroth maximal theorem and Pfefferman-Stein theorem. So let me introduce sharp function and maximal function and Hardy-Rideroth maximal theorem and Pfefferman-Stein theorem. Let F be a collection of balls or cubes. And for a measurable function h, we define each sharp function like this, and the maximal function like this. Then Hardy-Rideroth maximal theorem says that if p is bigger than 1 and Lp normal of h is finite, then Lp normal of h and Lp normal of its maximal function are equivalent. That is, there is positive constants N1 and N2 satisfying this inequality. And Pfefferman-Stein theorem says if p is bigger than 1 and Lp normal of h is finite, then Lp normal of h and Lp normal of its sharp function are equivalent. Similarly, we can define maximal function and sharp function with weights. Here, we change the measure, Lebesgue measure, to weighted measure mu, and here we also change the Lebesgue measure to weighted measure mu. Actually, Professor Pfefferman and Stein proved their theory in quite general setting in Professor Stein's book, but unfortunately, our weighted Sobolev space doesn't satisfy their condition. So one needs to prove a weighted version of Hardy-Rideroth maximal theorem and Pfefferman-Stein theorem. And Professor Kyung Kim and Professor Gi-jung Lee proved a weighted version of the Hardy-Rideroth maximal theorem in this weighted Sobolev space, and a weighted version of Pfefferman-Stein theorem. So, and let me introduce some important theorem in each step. Here is Professor Kyung Kim and Professor Gi-jung Lee's result.
Where's omega?
Omega is here. Here, mu is the arbitrary number which is bigger than or equal to 2. So, in this estimation, we can make the first term on the right side small enough as much as we want. And because of weight, we cannot use any translation or scaling property here. So we have to estimate this inequality at each point and each radius.
What is the Q?
Q, here. Definition of Q. It's a not normal cylinder. Actually here we define BRA, this cylinder. This is ball. So QRTX is, definition of QRTX is here. we have a similar estimation for divergence equation. But here we estimated ux instead of uxx.
It's not divergent type.
Sorry?
Is it divergent type?
Yes, this is for the divergence type. Because the coefficient, it only depends time t, so it doesn't matter. But we estimate this estimation for divergence equation. And step 2, by using inequality in step 1, we can prove this inequality. As I mentioned before, we can make this term very small. And similarly, we can also get this inequality for divergence equation. Actually, here constant n doesn't depend on cylinder QR, so we can change the left side to sharp function. But here and here, we need some condition. U have to vanish outside some cylinder, which is contained in this collection. And finally, weighted version, we use weighted version of partition of unity. By using this weighted version of partition of unity and weighted version of Peppermans-Stein theorem and Hadamard-Meissner theorem and inequalities in step 2, we can finish the proof of our theorem.
What's QK?
QK? Actually, this is a typo. It should be Mexican QK. Mexican QK. Yes. Actually, this set. It should be this set.
Excuse me, question. What is when plus index plus means x1 is positive, bigger?
Yes.
And what is x to some power?
Yeah.
Is it x1 or?
Actually, we mean here actually measure mu, the power is positive. Yeah.
Positive. And what is x? X and dimension.
X1. I'm sorry.
X1.
Yeah, this is typo. Yeah, this is a
X1.
distance from the boundary in the F space. Actually, here the sharp function with weight theta minus d plus p. This is, and actually here the maximum function with weight theta minus d. Actually, this maximum function and this maximum function are different. The weights are different. Maybe thank you for listening.